Welcome to the Rich Report, a podcast with news and information on the world of big data. Today my guest is from Cloudera. We have Justin Erickson. He is a senior product manager at the company. So Justin, welcome to the show today.
Oh, thank you very much.
Well, thanks for coming on, Justin. You know, I've read some things about Impala from Cloudera, but I thought this would be a good chance for us to look at some slides, and then maybe we'll do a Q&A at the end. That sound good?
Sounds great. Sounds absolutely great. Yep, we are very excited about the Impala project. We just announced the general availability of the project on April 30th after being in a public beta since October of last year. So it's been quite an exciting journey for us. So if we look at Slide 2, I'd like to run through a few topics that I thought would be of interest to everyone. First, I want to start with why Impala, why is it interesting, why is it getting the attention that it is currently getting from the market. The next piece is go into how does it work and walk through a query as it goes through the Impala system. And then I'd like to talk about some real-world use cases to make the technology come to life and talk about what it is been able to achieve through the beta program. And I often get a lot of questions of alternative approaches. Since we announced the Impala project, there's been quite a lot of attention and quite a lot of alternatives put out there, and wanted to talk about some of the alternatives that we evaluated and why we decided to take the architecture that we ended up with. And then ultimately, I'd like to wrap up with where is this all going? That Impala is quite an exciting and major development in the Hadoop ecosystem, but we see this as part of a bigger story that's playing out here, and I'd like to talk about how we see the platform for big data growing as we go forward. So if we take a look at Slide 3, I'd like to sort of level set with Impala in the context of Hadoop. It is very much designed to be part of the Hadoop ecosystem, so I'd like to capture what do we see at Cloudera as the core value props that is making Hadoop become the de facto standard for big data. So I see it boil down into three main areas. So scalability of the platform. Obviously, if I'm talking about big data, when I'm talking about the potential to grow into petabytes of scale, I want a system that can simply scale by adding machines. I can start with 10 machines or so to begin with, and I can just throw machines at that system as my data and processing needs grow without having to think about fundamental re-architectures or traditional challenges of scalability. Of course, that means in order to achieve this, that frameworks such as MapReduce, and as we'll get to with Impala as well, need to be designed for local processing. Adding machines gives you the raw hardware capabilities. But if I do not have a system that takes advantage of local processing, I'm shuffling around big data across the network, which would then make the network become an increasingly a scalability bottleneck as the size of my system grows. And of course, Hadoop, primarily with MapReduce and with Impala, has been designed to take advantage of local processing so networks do not become a bottleneck as the size of your cluster moves from tens to thousands of machines. The next point is around flexibility. And this one, I came from the traditional database world, previously working at Microsoft in the SQL Server group. This one took me a little bit to really grasp, but now that I see it in practice and at customer sites, I actually see this as the strongest of the three pillars. So the flexibility means that you can store all types of data. You can store your inherently structured tabular data. I can store data that what I would call semi-structured, where of course the data has structured, but I haven't actually gone through the effort of defining exactly what that structure looks like at the time that I'm loading in the data. And then of course you have unstructured data, things like images and videos, which has a binary encoding, but I'm not going to be running processing frameworks that take a look at tabular type data. The key piece of this I actually see is a decoupling of the storage from the analysis. In your traditional world, I would define what the data looks like before I go and store it, and then I would store that into that structure, and that make it easy for me when I want to analyze it that I know exactly what that structure looks like. In the Hadoop world, those two events can be decoupled. I can store anything up front, and at the time that I want to analyze it, of course I need to know the structure, but I can define the structure on the pieces of data that I find interesting for my analysis at a later point. An example customer of ours came to us and said, hey, I know I'm storing all the right data. I've captured all the data. This is in the biotech area. I know I've captured all the data from the experiments that are going on in customer sites around the world, as well as the research experiments that we have going on in R&D. I just need to figure out how to open this up to my researchers so they can take advantage of that. And that is something that is fundamentally enabled by the Hadoop platform. The last piece, of course, if I'm talking about big data where I'm looking to store data in case I may want to go and analyze it, I need to be able to do this at a cost-efficient price point. I'm not going to store petabytes of all my raw and granular data at traditional data management costs. And so you get the storage, the cost efficiency from the software itself, the fact that it runs on industry standard commodity hardware, and a framework where you get unified storage, metadata, and security, where it starts breaking down some of those ETL data transfer pipelines, where in the old world, you would move data between lots of systems, each system built for a particular use case. In this new world, you start seeing the data itself having gravity, where the processing comes onto the data, does local processing directly against the Hadoop data sets, and as the Hadoop clusters grow, you get more and more processing frameworks built up around this. So for those of you that have been in the Hadoop space for a while, I'm sure that was a recap of what you already know about the technology. So let's move on to slide 4 and start talking about the exciting new technologies with Impala. So first I'd like to talk about what's Impala. And the key thing that Impala enables is interactive SQL directly on top of Hadoop. There today is a technology called Hive that's built for batch processing on top of the batch processing MapReduce engine. And Impala gives you orders of magnitude faster performance than Hive. Of course, in any system, faster is always better. But what makes Impala so exciting is that it actually is fast. It makes a speed gain that fundamentally changes the way that users can interact with big data systems. So when using technologies that are built on MapReduce that do batch processing, you're typically looking at response times in minutes. If you are interacting with a computer system that's giving you responses in minutes, I fire off an analysis, either through a BI tool or through a SQL query directly. I'm not going to sit there and wait there idly for minutes for that response to come back. I will context switch to something else during my day, and hopefully at some point later in the day I remember the query that I sent off, come back and look at the results, context switch in what I was thinking, and figure out what I want to do next within that. And those context switches make it very difficult for you to iterate and test out hypotheses and get a traditional analytic or business intelligence experience against the system. Now when you move from the minutes to minutes of Hive and MapReduce to seconds, I can actually execute a query, wait for a response, look at the results, and iterate with the system in real time, which now makes it very possible for me to do traditional forms of business intelligence and analytics that previously were incredibly painful to, in many cases, customers would determine that that is just not a feasible way for them to conduct their job. Impala provides a SQL interface. It's approximately ANSI 92, which is compatible with what exists within the Hive SQL today. This makes it possible for the hundreds or thousands of users within traditional enterprises that know SQL to be able to interact with the systems directly, and makes it possible for BI tools to move over. In fact, one of the things that is sort of a testament to how much of a compliance we built within the SQL standard here is one of our earliest private beta customers was a big user of a BI tool, in their case MicroStrategy, were so excited by the results that they were seeing with the Impala project that they took MicroStrategy and pointed it at Impala before we had the opportunity to brief MicroStrategy on the Impala project, and it just worked for them. Of course, there are opportunities for us to integrate a little bit deeper, but that shows the level of SQL standards compliance. When you look at the first two bullet points, there are, of course, systems today. They'll give you interactive SQL, and actually will give you your traditional data warehouse technologies, will give you faster levels of SQL. They'll give you higher levels of SQL compliance. What makes Impala unique and exciting is the fact that it is natively built on Hadoop and H-based storage and metadata. So your traditional database technologies have a query engine, a storage manager, and metadata store that are very highly coupled to give you the maximum performance. It figures out, load the data, what is the most optimal way to load that data into the correct structure, the indexing to build around it, the partitioning to build around that, to maximize for the query response times. That does well when I know exactly what I'm going to ask of the systems, but does not do well when I'm trying to go and explore new and big data systems. Impala, on the other hand, gives you the query engine where it does not have a storage manager of its own. It uses the existing Hadoop HDFS storage, and you can also use HBase if you so choose. It also uses the same open Hive meta store. So that means for Hadoop users, they can define what their data looks like once and have it available both for their interactive SQL as well as for their batch processing through traditional MapReduce-based engines. Ultimately, the same value props that I was talking about before, the flexibility to store the data without having to define anything about it, and then at the time you analyze, define the schema on top of it that gives you the flexibility, the scale advantages that we'll get through in the architecture, and of course the cost advantages, all still apply for Impala. It's been designed to be a part of this ecosystem. This means, unlike traditional engines, there's no need to duplicate or synchronize the data and metadata between multiple systems, while Impala still maintains the local processing against that engine to avoid network bottlenecks. Impala is built to be a strong complement to MapReduce. So MapReduce is designed and great for batch processing. I often use the analogy of a dump truck, that it is great at moving large volumes of data around in batch mode where I want to go and take 10 terabytes of raw data and maybe like sessionize web clicks or build out my dimension and fact tables that's going to power the daily reports from my data warehouse. MapReduce does a great job on that. Impala, on the other hand, is like your Ferrari engine, very good at nimbly getting to the quick answers you're looking for. So it's purpose-built for low latency SQL queries directly on Hadoop. When we look at the benefits of why customers are excited about this, by far and away, this comes down to more and faster value from big data. So as we talk through that example of the minutes to tens of minutes response times through batch MapReduce-based engines and Hive, that really made BI pretty impractical for most users. And what you'd end up seeing is these large Hadoop clusters with petabytes of information, many hundreds or potentially thousands of nodes clusters, where you'd have tens of users who actually understood the implications of what they're running or could build MapReduce-based jobs against the system. Now with not only SQL but interactive response times, you can open up this system to hundreds or thousands of users within your companies that are trained in SQL. And this basically gives you more users and for existing users faster value from the system. It maintains the same flexibility, so you can query across all your existing data. When you install Impala, it does not create any new data structures. It just runs directly on your raw text files. It does also provide best-of-breed file formats. In the end, what we really see this come down to is the ability to run multiple frameworks on exactly the same data at the same time. So I can run my MapReduce-based engines to do my batch processing on the same data at the same time I'm running the Impala SQL queries on those raw data sets. And of course, it maintains the cost efficiency that makes it possible to keep your full fidelity data so I do not need to resort to sampling. When we look at slide 6 to talk through quickly on the architecture of the system and how a query moves through the Impala engine, this slide shows an example of 3 nodes within your Hadoop cluster at the bottom. So you see HDFS DN stands for HDFS data node, so that's a data serving node in Hadoop. I also show HBase here. The story remains the same whether or not you have HBase involved. So you can, if you're not using HBase, you can cross that out. If you are, it's the same thing as interacting with the data node. In light blue, I show what is new and installed with Impala. So on each one of the Hadoop nodes, you have this Impala daemon that has 3 architectural layerings of the planner, the coordinator, the executor. Overall, each Impala daemon serves 2 goals in life. First purpose is it takes SQL requests and distributes them out across the cluster. The second purpose is every one of the Impala daemons can also execute queries that have been initiated by other nodes. In the upper right, I show the unified metastores. So you have the Hive metastore, which this is the open metastore that enables you to define schema on read. So I can store the data up front, and through this store I define after the fact what the data looks like, and this enables the translation of SQL tables to the files and directories and the structure within those files that defines the columns within that. It has the HDFS name node that takes the files as defined as stored within the system and maps out where the data is actually located across the distributed cluster. And then we have a state store which is installed with Impala. This deals with the membership resolution. So when new Impala daemons come online, they register with the state store, and the state store informs the rest of the cluster of the overall membership. Well, it looks like a single point of failure at first glance. It's designed such that if the state store fails, queries continue to run. They'll just run on the previous view of membership, which means new Impala daemons would not be able to register with the rest of the cluster until the state store comes back online. So if you look at a query running through the system, the query will come in through traditional SQL app, let's say your BI tool of choice, through ODBC, JDBC, remains the same through our GUI interface or a command line shell. Just like any other engine, it submits a SQL request. If we look at slide 7, the planner will take that query plan using the data from the Hive metastore and the HDFS name node. It can determine how to take the complex plan and distribute that out across the cluster, such that the plan fragments are running local to where the data exists. So when it does things like filtering and joins, that will happen on each one of the local nodes. If we look at slide 8, the query executors will then execute those plan fragments against their local data sets, and will start streaming results back to the end clients. This, in the Impala architecture, enables us to have flexible multi-stage pipelines. In this case, you see a 3-stage pipeline, and results can be streamed back directly from in-memory transfers, avoiding unnecessary I/O, which would make sense in a longer-running batch processing engine. When we run across our clusters, the Impala processes are able to very effectively drive the hardware. So we see in our larger cluster tests when we're running queries that we're running about 80 to 90% the I/O throughput on the raw disk, which for industry standard commodity disk, that's typically 100 megabytes per second. We not only know what data exists on which nodes, we also know which data blocks exist on which disks. And we can leverage this to only have 5 millisecond queues on our I/O subsystem. So we're not just oversaturating the I/O subsystem. We're very effectively able to pinpoint what data exists in which nodes and drive the I/O subsystem to the maximum performance that they can go and achieve. When you look at a traditional Hadoop node, you're looking at 100 megabytes per second per disk on average, you look at like 12 disks per node, you're looking at 1.2 gigabytes per second of data that can be read. And of course, Impala will do what it can to only read the sets of data that are most relevant. So if partitions are defined, it can take advantage of partition pruning, but not necessarily a requirement. And that's where a lot of the performance comes from. So if you take 1.2 gigabytes per second per node of data that can be read and processed through the query engine, you multiply that by, let's say, 100 nodes, you're starting to talk about some pretty amazing performance at very large scale. If we look at slide 9, to summarize what we just saw, when we look at Impala compared side by side with its complement in the batch processing side called Hive, Impala shares everything that's client-facing with the Hadoop ecosystem. So that metadata store is open and available to not just Impala, but for Hive, for Pig, for MapReduce, and so on and so forth. It uses the same ODBC and JDBC drivers that enable SQL connectivity between Hive and Impala. Uses the same ANSI 92 SQL syntax as the Hive project. Underneath it all, it has the same native and open flexible file formats as Hadoop. Uses the same machine pool, and if you're using our GUI experience, uses the same Hue GUI. So from a client experience, everything that I see from how I connect, the tools that I use, the language that I use, and the data that I'm talking to is shared. I just change the connection string to connect to this new engine, and now I get an engine that's built for a different purpose. Hive is built for batch processing on top of MapReduce, and then Impala is a native MPP query engine, where we took the heavy engineering of building this out. In the interest of time, I will talk through a couple of customer use cases at a very high level, but I want to make sure that I get into the alternative approaches and where this platform is going. So when we look at the Impala use cases, as you can imagine, this really boils down to interactive BI and analytics on more data now becoming practical, where I not only get SQL, but I get interactive response times. With this, when I'm looking to ask new questions of the data sets and explore new structures, this becomes particularly valuable, where I don't have to go and go through the ETL processing to store all the data in a traditional rigid architecture in order to analyze this. Oftentimes, we actually see this as being complements, where people are exploring and finding new insights on their data in Hadoop with Impala, and then they'll operationalize that within their traditional data warehousing architecture, so they can track that new metric or that new insight on a regular basis. Likewise, they can use Hadoop to be the archive, whereas before you take the traditional data warehousing architecture and you back that up to tape, put it in a cold dark closet and never see it again. Now with a cost-effective platform like Hadoop, you can actually store the full granularity of data and the full history of your data within Hadoop. And occasionally we see customers that are moving from batch processing to continuous ingest, where they see, even though it is not an interactive human response time, they're finding that the overhead of the batch processing engine with MapReduce is that startup time is becoming more costly portion than the data processing itself, and moving on to Impala can help with that. So just quickly, we have one of our earliest beta customers was a global financial services company that was looking to move to longer history of data. They currently captured a year of data in their data warehouse, and they wanted to expand on to 2 years and beyond to do things like fraud detection. So of course, there's the easy fraud where somebody steals your account and goes and makes large purchases or large deposits from, or takes out large withdrawals from your account. That's clearly something you're going to want to go after. But more sophisticated fraud, where somebody steals many, many different accounts and will go and steal small amounts of money from each one of these accounts, poses an interesting fraud challenge. Clearly, a large financial institution is not going to want to go after every time somebody steals $20 from an account. But if somebody steals $20 from hundreds of thousands or millions of accounts, that then becomes something very interesting to go after. And doing that over a longer duration enables you to see that longer trend lines. But for them, they were stuck between a rock and a hard place, that an additional second year and beyond is inherently less value than the first, and they didn't want to double their data warehouse spend or data warehouse footprint to be able to go and do that. So now with Hadoop and Impala, they can get that same experience that they got in that first year on the second year and beyond to be able to explore those relationships. When we look at slide 12, 6.3 systems, also in a similar boat, that they were looking at storing decades of information and finer granularity of data than what they were able to do before. And as they brought in more and more data sources, they did not want to deal with the cost, both in terms of the raw software license and hardware costs, as well as the people cost of loading these data sets into the traditional data stores. In slide 13, Expedia, very similar boat, that they were looking into moving to more granular sets of data, moving from, for example, the bought and sold purchase transactions to the omniture logs of users moving through their website and seeing the behaviors that led to purchases and the behaviors that led to disengagement from the website, and found that was more flexible data sources where it was defining rigid structure on that became costly. And then, as you can imagine, you look at the number of clicks that a user does on the website versus the number of purchases that they do on Expedia, we're talking about exponential growth in data sizes that they were just too costly to consider there. I'd like to wrap up with talking about our design strategy, contrasting that to alternative approaches, and then talk about the path going forward, and then we can open up for some Q&A. So if we look at slide 14, our design strategy with Impala is another processing framework designed to be intimately part of the Hadoop ecosystem. This means you have one pool of data in their native and flexible file formats without having to do conversions. You have one metadata model that I don't need to define my data for Impala and define my data separately for the existing Hadoop processing frameworks such as Hive and Pig. One security framework across the platform so I don't have two different systems cobbled together. And of course, underneath this all, one set of system resources that achieve that linear scale through local processing. When we look at slide 15, there were many other alternatives that we evaluated before we decided to go and take the heavy engineering effort of building an MPP query engine integrated into the Hadoop stack. And you see, for those of you tracking the Hadoop ecosystem, you see vendors that are filling in each one of these different alternatives, and actually you see a bunch of them moving and trying out multiple variants of these. So starting from left to right, the first and most obvious approach is, well, we have a SQL processing engine, and most processing around Hadoop has been built on top of batch MapReduce. Why don't I just make MapReduce faster and see if I can get interactive response times through that? Our view on this is MapReduce was designed from the guys at Google to be able to be a batch processing engine. So it's designed to maximize throughput on your long-running jobs. Of course, there are opportunities to speed up this engine, and that's greatness for the ecosystem in general. But it's moving against the design grain when you're looking to optimize for low latency on individual jobs above throughput across multiple jobs. And we see this play out even within Google. So Google still runs MapReduce today within their ecosystem. When they decided to build they needed an interactive query engine, they continue to run MapReduce, but built their Dremel project outside of MapReduce as they saw that was fundamentally designed for a different architecture. And we see the same will take place here, that there's opportunities to speed up MapReduce, and that's greatness for the overall ecosystem, but in general, designing against the design principles that make MapReduce great at batch processing paints you into a corner. The next approach, and oftentimes you actually see people that start with MapReduce offloading of processing and then say, well, if MapReduce is the bottleneck to low latency, why don't I just remove the batch processing MapReduce engine and use a distributed query technology that I built up thus far to use HDFS as an external file system. Most of the traditional MPP query engines while they have a tightly coupled storage manager, they have the concept of external tables where they can access external data sources for portions of data as necessary. The challenge that you get here is they have separate nodes that are running their traditional query engine and separate nodes that are running HDFS. And when they're doing these remote queries, they're just basically using HDFS as a dumb storage layer where they'll pull all the data that's necessary for a query across the network before they begin any processing. Works great for POC environments where I'm just doing small queries on small data sets. But as the data sets grow, and obviously big data, the name of the game here is large queries, large data sets, the network increasingly becomes a bottleneck as the size of my query grows. And then once the data comes into that processing engine, to their query engine, it then goes through a format conversion, which is also a CPU-intensive process. Great when I occasionally need to access data, but not great when I'm on every single query going and accessing Hadoop data sets. The next approach that you see people try, which was typically started with upstarts, new startups in the area that were there before, but now you see some of the bigger guys, and I anticipate more people to try this with their technologies as well, which is, well, let me take my traditional MPP query engine technology and lay that out side by side with the Hadoop stack. So I'm running on each one of the nodes, it's running the traditional query engine with the traditional storage manager and traditional metadata store side by side with Hadoop to leverage the same hardware layout. Challenge with this is I still have a tightly coupled storage manager with the query engine where I have to load the data into this specialized format before I can get any of the great benefits from performance. And so I ultimately get the same trade-off that I had before, that I can either choose to have the flexibility and scale and cost effectiveness of Hadoop, or I can load this into a traditional data warehousing engine, which is great for asking questions repeatedly, but I still have the same rigid structures, siloed data, and ETL. Once I load the data into that engine, even for some of these guys that are starting to actually put their proprietary file in HDFS, that file is not available for MapReduce processing and is not a native format within Hadoop. So I get the same downsides that I get in the traditional engine where my data is locked into one type of processing on top of that. When we look into how we designed Impala, our goal was to say, well, the MPP query engine portion, that's the right approach. So that from that siloed DBMS, the MPP query engine makes sense. But we don't want to force all data to be converted into a specialized format in order to gain performance. MapReduce is still very much a part of this story, that I need to be able to run MapReduce and Impala on the same data sets. And I still want to have the same flexibility where I can store the data up front, and then I can define the schema on top of that without having to go and change or reload that data, which delays me from being able to do the processing on those data sets. So while we look at the other three approaches, and we saw that they were cheaper ways of getting into something that was faster than what you can do with Hive, we believe in the long run that the Hadoop ecosystem is growing fast enough that it warrants the heavy engineering of taking over 2 years of engineering effort to build out the Impala project to have a native and purpose-built query engine for Hadoop rather than repackaging existing technologies. When we look at slide 16, you see a lot of the BI partners, both from traditional backgrounds, such as MicroStrategy and Tableau, as well as upstarts that have grown up around Hadoop, are building on top of Impala. This just captures some of the guys that were early on during the beta process, but at this point you basically name a BI vendor, and we are in discussion or working through validation with them. And I expect that it'll be very hard-pressed to find a BI vendor that is common within the marketplace that is not working on some form of integration with the Impala project. And lastly, I'd like to wrap up with slide 17. We've sort of touched upon this throughout the talk here, but as exciting as Impala is, and we do see this as a monumental leap forward for the Hadoop ecosystem, the story of Impala and the story of Hadoop is not just about reinventing SQL on Hadoop. When we look at the platform for big data, we see this growing as multiple processing engines that move towards the data to do local processing, basically the data itself having gravity, where I can run my batch MapReduce processing, I can run my machine learning jobs through like Crunch and Mahout, I can run interactive SQL through Impala. We also announced a deep partnership with SAS, where SAS can run directly against the Hadoop data sets as well. And I'd expect to see more of these engines continue to build out, where more processing moves onto the Hadoop ecosystem rather than the old world where you have stitched together systems. With this, I want that single platform, single data sets across multiple processing frameworks. Everything needs to be able to scale from tens of machines to thousands of machines to be able to deal with big data scale. Maintain that flexibility that I can store anything up front, and then for all the processing frameworks, define the schema after the data is stored. Of course, I need the cost structures where I'm storing at hundreds of dollars per terabyte rather than tens of thousands of dollars per terabyte that you get with traditional data management architectures. And then across this all, Impala itself is Apache licensed open source, and everything within our platform is Apache licensed open source. Enabling an open source platform makes it easier and more flexible for partners to integrate and more comfortable for our customers to be able to try out the technology, use it, and be rest assured that they are not getting locked into the traditional proprietary platform pricing structures. With that, I'd like to open up for any questions. I apologize we ran quite a bit longer than we anticipated, but I hope that that was a valuable overview of the Impala technology.
Yeah, thanks for that, Justin. This was very educational. So I did want to ask you more about the origins of this. Did you guys look at how things were being done and see that Hive was a bottleneck in that and attack that piece of it, or what was the story?
Sure. So there are two pieces with this. One is we saw what Hive and MapReduce were able to achieve, and we saw the growth of the Hadoop ecosystem. As more and more data came into that system, we believe that batch processing is not all you want to do with the raw and granular data sets. We saw, MapReduce was built for batch processing, so we saw that, yeah, we can make it faster, but you were just not going to be able to get that interactive BI response time on top of that. The other piece, in terms of the origins of the technology, is Google published the Dremel paper in 2010, and it is absolutely no coincidence at all that the paper was published in 2010, and shortly after that, we recruited Marcel Kornacker, who's built a bunch of query engine technologies within Google, to Cloudera and founded the Impala project. So it's very much inspired by what Google has gone and done with their infrastructure. Obviously, Google's built a very, very successful business driven around data, and we saw the architecture that they chose and saw that that was just fundamentally the right way of building things, where you have the common storage platform and multiple processing frameworks on top of that.
And I wanted to ask you a little bit about security, Justin, because you brought it up on slide 14. This has been a criticism of Hadoop frameworks for a long time now. By re-engineering this, did that give you the opportunity to build in good enterprise security?
Yeah, so part of the security story comes into two areas. One is when Hadoop was first built, it was built for running within companies like Yahoo and Facebook, where they kind of wanted to just give everybody access to all their sets of data. So security wasn't top of mind for them from the beginning. Over the past, actually about, let's say, a year and a half ago, security was added in as a first-rate feature within Hadoop. And so you have even before Impala was added in, you had the ability to do Kerberos authentication against your system, so you know who the user is, and you could go and provide file-based security, so you can grant users read-write access depending on what they have access to, so I can lock people down. Going forward, we see the ability to have this common metastore enables us to actually then also define common security across that platform. So I can define more granular sets of security through the common metastore and have multiple processing frameworks to respect that level of security, which would not be possible with cobbled together systems. So by building all the components to interrelate with each other, it makes it possible for us to move the watermark across all the platforms together in a coordinated fashion, rather than having a security for your SQL engine and security for your batch processing engine as being separate in each one of these processing frameworks as having separate levels of security. So I say that was an early knock that, yeah, absolutely, way back when Hadoop first came out, it really didn't have security. About a year and a half ago, it actually does have a good amount of security, and you see a lot of traction in enterprises such as traditional financial enterprises that security is top of mind, and they are running Hadoop today. But I think that story will continue to improve, and by designing Impala to be part of the overall ecosystem, it makes it possible to define a unified security platform in a way that is going to be very difficult for side-by-side systems to achieve.
Well, great. Well, Justin, kind of a wrap-up question here. The fact you went with open source for Impala, what would you foresee? What kind of innovation would you foresee from partners and people that take this technology to the next step?
Absolutely. So I see there's going to be, in general, there's going to be two types of innovation that's going to come through with this. One is you're already seeing your traditional engine, your traditional technologies, such as Tableau, MicroStrategy, that have worked well against your traditional data warehouses, be able to integrate directly against Impala, integrate at lower levels, taking advantage of things. We'll see. I imagine we'll see more people take advantage of the metadata of Hadoop within those higher level platforms. I think we'll also see technology that may get built up from your existing technologies and also new upstarts that will find ways of taking advantage of different stages within the pipeline. I think there's an area that's ripe for opportunity, and you're seeing a lot of innovation there of how do I take that raw data sets. Even though I can store anything up front, when I analyze it, I still need to figure out what the structure of that looks like. And I think there's a lot of opportunity for innovation in that space of how do I figure out what the schema of those data sets look like, and that's something that becomes possible because every stage of the Hadoop platform is open source, and you can integrate and look deeply within the system in ways that would not be possible in closed platforms.
Yeah. Well, Justin, I want to thank you once again for sharing this with us today, and thanks again for coming on the show today.
Thank you very much.
You bet. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on the world of big data.